Welcome to today's webinar. I'm Kent from the Quantum Product Management team at Zurich Instruments. We're part of the Rodenschwarz family, specializing in quantum control solutions and lock-in amplifiers, and our products are used for a broad spectrum of experimental research and technology applications. Today, my colleagues and I will walk you through how to use our updated software framework, LabOne Q, and how it fits the way you work in the lab. We'll introduce workflows which take you from qubits to pulse sequences to data handling and analysis, all combined together in a streamlined way. To demonstrate this, we'll be doing a key part of a superconducting quantum computing experiment, Qubit tune-up. And we'll also discuss how the LabOne Q software architecture helps you tackle your next quantum research challenges. I've brought along two guests today, Stefania Lazar, our expert on the experimental side, and Simon Cross, our expert on the software side. Steph is the product manager of the LabOne Q applications library, and she holds a PhD on superconducting qubit research from ETH Zurich. Simon is the lead software developer of our quantum applications software team, core developer of the Q-tip package for simulating quantum systems, and a member of the OpenQASM Technical Steering Committee. We'll be running remotely on a tunable transmon QPU with the group of Professor Andreas Wallraff at the ETHZ-PSI Quantum Computing Hub, part of our joint Innosuisse Sherlock collaboration project. To wrap up, we'll have a live Q&A session. Feel free to use the Q&A button to pose questions, and we'll try to address as many as we can. Let's dive in. Hey Steph, thanks for joining. So today we're running at the ETHZ-PSI Quantum Computing Hub, and on their setup, so this is a setup with flux-tunable transmon qubits, and we're running with our qubit controller, the SHF-QC. And Steph, can you tell me what we're doing today?
Yes, Kent, thank you. Thank you for having me here. So today we will do a tune-up of a single qubit, a tunable transmon qubit on this setup.
Yeah, and why do I want to do a qubit tune-up? What does that mean?
So a qubit tune-up you want to do when you get a new processor, right? You want to operate to do your quantum computing experiments, quantum computing algorithms on this new processor, but first you need to tune up your qubit. So you need to find the parameters of these qubits, the frequency, the pulse parameters to implement quantum gates to then write your quantum computing algorithms.
Cool. And so what's the important part of qubit tune-up? So what are the different pieces I need to do it?
Yes, so of course to do a tune-up you first need qubits, right? So this you get from your fabrication. And then you would need the right hardware to control your qubits, which we provide, as you mentioned. And then what this webinar is about is the right software tools. So in this case, we introduce to you our new tools in LabOne Q.
Cool. Can you tell me more about this? So I see we have this page open, the LabOne Q applications library. And so what have we introduced that's new in LabOne Q that's useful to our customers?
Yeah, so I'm really excited to tell you about this. So we've tried to add a different perspective to writing your software for quantum computing experiments with LabOne Q. So we've tried to focus it on creating experiment workflows using qubits and quantum operations, which are like quantum gates. And this, I will go on to tell you a bit more how this is actually constructed. So you see here in this picture, we use these workflows, which is a new feature in LabOne Q. And the workflow is really just a parser of Python functions, which we call tasks. So here they're shown in blue. And so all of our experiments that we have written in this applications library, so this is a new package that we've launched to showcase how to use these workflows and the quantum operations and qubits. So all of these experiments, the experiment workflows create a pulse sequence, then they compile it, they run it, then there's an analysis step, which is not shown here, and then you can choose to update your qubit parameters on the QPU that you define in your software, and then move on to the next tune-up experiment, for example. And
yeah, so each of these workflows then they can either run standalone with all of these parts, or then I can connect them together. I guess that's the image on the right-hand side here.
Exactly. So this is going a bit towards automation. So you can also wrap workflows within a workflow and essentially execute a series of experiment workflows in a certain order to tune up, for example, the full processor.
Great. So let's look at the first experiment that we're going to start with. So this is Qubit spectroscopy. So this comes after we've done the resonator spectroscopy experiment. So now we have a resonator line. So what we see on the right-hand side of this is we have a resonator line coupled to a qubit. And on the left-hand side, we have a graph that shows the amplitude and phase on the y-axis, and then the frequency of the resonator line on the x-axis, with the frequency response of this resonator changes in the presence of a qubit in the ground state and a qubit in the excited state. So what we're going to do in the qubit spectroscopy experiment is we're now going to sweep the drive frequency of the qubit, and we're going to sit at this dotted line, so just at a single frequency in the readout resonator. And what will happen is as we change the drive frequency of the qubit, we're going to get a change in the amplitude and phase response of the readout resonator, and we'll show that. So the graph that you're going to see in the analysis will actually be not this same frequency, but the swept drive frequency of the qubit and the amplitude response.
Exactly. Thank you for that explanation. So let's see how we can use the experiments in the applications library and the new features of LabOne Q to implement this small tune-up experiment.
Yeah. So here we're actually running at PSI remotely. So these are on live qubits, right?
Exactly. Yeah. So we're connected to this setup, and here I have some imports, which I will not show. And then the device setup is created here. This is an object in LabOne Q. And it connects the instruments in the rack at the ETHZ-PSI setup. And then I want to show you really the components that are new and that are needed for this for the applications library, the experiments we've implemented there. So let's start with the QPU, so the quantum processor. And you could define it from scratch, but here, because we've tuned up this processor already, we have a JSON file somewhere saved on the computer, and we can load back a QPU with fully tuned up qubit parameters. So here there's a path which I've defined above somewhere, and we import these serializers from the LabOne Q package and obtain our QPU. And then the QPU has qubits. In this case, the chip at the setup contains 3 tunable transmon qubits, pairwise coupled. And here I just assign them to this variable so I can work with them a little bit easier. And each of these qubits has, these qubit objects reflect the lines that are actually on the QPU. So these qubits have a drive line, and then a drive EF for exciting the F transition, a measure line, an acquire line for measuring the qubit, and a flux line because it's a tunable transpon, so you can change its frequency, but we will not show that here.
Great. So now we're going to connect to the setup. So the session in LabOne Q just handles the instrument communication. And here, because we're running on a real setup, we're not using an emulated session. But if you would like to also get started using the software, if you don't have it already, you can go. It's Apache licensed. You can download it, use it for free. And it has an emulation mode where you can emulate the instrument itself and run without connection to any hardware.
Yes, and that's very useful for prototyping. You don't always have qubits at your disposal, right? But you do want to prepare your experiments offline. Then the next important component in the new features of LabOne Q is this folder store. So the workflows, the experiment workflows, can automatically save your data in a folder that you've specified if you activate this folder store. So we will do that here. And you can deactivate it by deactivating, then you say you do not want to save your data, but let's activate it for now. Then, yes, let's move on to qubit spectroscopy. So that was very nicely explained, and let's see how the code implements that. So we have here the qubit experiment module, And inside there's an experiment workflow. And the package here allows us to inspect the source code of any of these workflows. So you can see how it's actually implemented. So here is the experiment workflow function. And the input parameters here are quite standard across the experiments. So the first input parameter is a session that we've instantiated above, a QPU containing the ground truth of this experiment, so the qubits with their parameters, which we've also defined above. Then the qubits on which to execute this experiment. So these are a subset of the qubits on the QPU, or all of them, depending on your choice. And then we have the sweep points. So here are the frequencies of the qubit excitation signal. And then temporary parameters. These are very useful because the qubits, as I've said, their parameters really define our best knowledge of the system. And you want to carry that around and not modify it all the time and forget that you've modified something temporarily. So for that, we have this feature where you can pass some qubit parameters that you want to change only for this experiment, without affecting the ones in the QPU. And then finally, we have options, which allow you to tweak other things about this experiment workflow, which I will show a bit later. So, and then as I've explained in the beginning, the tasks inside this workflow are the ones that create the experiment sequence. Then they compile it. Then there's a task for running it on the hardware or in emulation mode, running the analysis workflow. So this is yet another workflow inside this experiment workflow. And then optionally, you can update your qubits with the parameters found from the analysis.
Great.
Good.
So this is the source code that I can look at for the workflow execution itself, but I can also look at essentially the sequence of the experiment.
Exactly.
And that's what this next cell is, I guess.
Exactly. That's the next important part that I want to really focus on from all these tasks is the create experiment, because here we create the pulse sequence for this experiment, and this also has the same input parameters more or less, so the QPU, the qubits, the frequencies, and the options. Then there's the big doc string here for you to know what is being done, some validation, which I will not go over. And then this new concept, this new tool that we've introduced that lives in the QPU, the quantum operations, a set of quantum operations that we've defined. And these are then used within the normal LabOne Q acquire loop, real-time acquire loop. Then we iterate over the qubits and the frequencies for each of the qubits. We write a little sweep for each of them to sweep over the drive frequencies. And then we just call a set of quantum operations. So it's intuitive, it shows you the physics here. We want to set the frequency to this sweep value for this qubit. We apply a spectroscopy drive on this qubit, we measure it, and then we do a small passive reset the delay for which you can choose here. So what I want to say a bit more about these quantum operations without going into too much detail, but how they work is that they inspect these parameters of the qubits. So the qubits have many parameters here, as you see, their lifetimes, coherence times, their frequencies, and then also drive pulse information. So for example, the spectroscopy drive operation knows to inspect these two parameters of the qubit, defining the length and the amplitude of a spectroscopy pulse. So in this case, we are going to apply a constant pulse of 5 microseconds with this relative amplitude scaling relative to the output range of the instrument. Good. So this is what the experiment does. It's quite concise. Then the other part of the workflows that is very useful is these options classes. So you can obtain them. Every workflow has its own options class. You can take them from just like that, from the experiment workflow. And if we print them, you see now the tree display of this for each task, what options there are. And the create experiment task that we've just looked at has several options for how to do the acquisition. So in this case, the number of time to average, what type of averaging to do. In this case, we do cyclic averaging, and the acquisition type, we do an integrated average. And to change these options, you would set the value like this, like in a call way, like calling a function. So here we set the spectroscopy delay to 1 microsecond to give a bit of time between driving and exciting the qubit again and the measurement. We increase a bit the number of averages just for better signal-to-noise ratio. And we say we want to update the qubit parameters with, so the qubit frequency that we've tuned up with the value found from the analysis. So let me run this. Then let's choose the qubit on which we want to do the experiment. So now I just chose this index 2 of so the third qubit here. And as I've said, we've already tuned up this processor, but just to show you, if you hadn't and you just know a good guess value from your measurements in fabrication or so, you can put it here in the qubit parameter. And we see that it is set. And then we run the experiment workflow. So as I've said before, here I want some qubit temporary parameters because I want to reduce the power a little bit. So when you do most of your pulsed experiments, when you do right quantum circuits, then you want a lot of power. So we usually this is set to a very high value, like 10 dBm. But here for spectroscopy, we reduce this power a little bit. Then we sweep 20 plus minus 20 megahertz around our best guess of the GE transition frequency. And we start by instantiating the workflow parser, which just essentially resolves the dependencies of the tasks inside. And then in the second call, we run it. So let's see what happens.
Yeah, let's look at it.
We get a lot of information about what's going on. So all the tasks that are started, ended, time at which this happened. So you can track everything that's going on. The actual execution time was 6 seconds. And then the analysis runs here. So all of these are the tasks of the analysis. And before I show you what is actually saved and the plots, just to demonstrate that we've run this with update equals true. So then the qubit frequency was changed to the value we got from the analysis, which we
So without
check.
even looking at the plots, I can have the analysis run automatically if you have a standard analysis, and it can already update the values for you.
Exactly. So with this, you could already move on to your next experiment. But let's just see what was saved. So this is the folder that I've specified above in the folder store. And we have today's date. And inside it produces a timestamp when the experiment has started and the name of the experiment. So now it says qubit spectroscopy. And here you see there are many JSON files and PI files for the inputs and the outputs of the tasks inside that were run. And in particular, you have your QPU that was saved, the qubits, so you can always load these back, as I've done in the beginning of this tutorial. And then the plots that were generated by the analysis. So here we see what Kent very nicely explained. The qubit drive frequency on the x-axis, the transmission signal, so it's the magnitude of it. And we see that we've centered it around our best guess, but the real frequency of the qubit was a bit lower at 6.58, and we've extracted it from a Lorentzian fit to this dip. And the new values are displayed here for you on the bottom with the previous value as well for reference, just to see how much the frequency has changed. Good. Then, yes, I think we've now calibrated our qubit frequency. So the next step in the tune-up, normally once you know your resonator, your readout frequency of the qubits and how to excite the qubit, you want to know how to drive the qubit transition. So how to go from this ground state to the excited state. And for that, we use an amplitude-Rabi tune-up experiment.
Exactly. So in our manual here, we have a cartoon of what this looks like. So on the top here, we have the block sphere with the vector representing the qubit state pointing. It can start along, let's say, the ground state, which is this 0. And then as you apply a fixed pulse length of differing amplitudes, you rotate this vector into different parts of the block sphere. In this case, we're rotating around x. And as you apply larger and larger pulse powers here, then you traverse the sphere farther and farther. And eventually, you then make a sinusoid because you're rotating the vector around the sphere. And what we'll see here is that we generally want to tune up 2 specific pulses, namely the pulse that goes from pointing from the ground state to 90 degrees, so then in the plane, and then the 180-degree pulse where we go from the ground state to the excited state.
Exactly. And this we can all do with one experiment written in the applications library. So let's have a look at how this is implemented. Let's directly inspect this create experiment task, which creates the experiment pulse sequence. You see that the inputs are as before for the Qubit spectroscopy experiment. The only change is that now we sweep amplitudes and not frequency, so the drive pulse amplitudes that you can pass in here. I scroll through the doc string and the validation that we have in the beginning and go to the acquire loop, which is as before. Then there's a sweep across all the qubits. So this can be done in parallel. If you pass a list of qubits here, you can execute this Rabi experiment in parallel on all these qubits. And this is what the sweep does here. Here we also have the option to run the experiment with active reset. You can activate this from the options. We will not do it here, but you can, if you've tuned this up, you can easily enable it in all of the experiments where it's relevant.
Yeah. So there you just need your state discrimination already calibrated, and once you have your state discrimination, you can use this active reset operation in any of your experiments.
Exactly. Good. And then we create several sections. So as I said, this is done in parallel on all the qubits, and we want to get the timing right and the alignment right. So this is what all these sections are here about. So we have a big section, and then the drive section where we iterate over the qubits and the corresponding amplitudes. And we call a prepare operation. So in case you're tuning up your EF transition, you first want to prepare the qubit in the excited state and then do the Rabi on the second excitation. Here we do it on the G, so just we do not prepare anything. Then we apply this X180 operation, which is the one we want to tune up. So here it's almost like a placeholder for the fully tuned up one, but we sweep its amplitude. So exactly, so we use this operation and sweep the amplitude for it, and then we measure. So we create a measure section on all the qubits and call the measure operation, and then the passive reset, which we now use. It's about 200 microseconds to let the qubit relax back into the ground state because we do not have active reset at the moment. Another thing here is the calibration traces, which you can enable from the options. And these are just reference states. So you say you want to measure your qubit when it's prepared in some reference states, like the ground state or the excited state, such that then you can project the rest of the data from the experiment on the line in the IQ plane between these points in your raw data. And then from that, you can infer your qubit population. Of course, for a Rabi, this doesn't make so much sense because you're tuning up the pulse, but because it is already tuned up, we enable it in this experiment just to show you what it looks like.
So users of LabOne Q already are probably familiar with our pulse level syntax. This is very similar, but now at a higher level of abstraction, focusing on the qubits and their quantum operations. If you're already familiar with it, it's a logical abstraction, so there shouldn't be a huge learning curve here. If you're yet unfamiliar with LabOne Q, either at the pulse level or at the gate level, we're happy to help you get started, and you can reach out to us with questions.
Exactly. Maybe one more thing I wanted to say here about how say it again, how these quantum operations work. So the X180 operation looks at the following qubit parameters to know how to apply this drive pulse. There are parameters here that start with GE drive or EF drive, depending on what we chose to calibrate. In this case, it will look at these parameters and apply a pulse this long, 51 nanoseconds. And the pulse is here a drag, a derivative removal by adiabatic gate pulse shaping technique, which is used to correct for phase errors or leakage.
Yeah, so in the cartoon, you saw a Gaussian, but as Steph nicely just said, there are many other pulse shapes that you might want to use as your preferred pulse shape for your control pulses. And a lot of them are already in our pulse library, and you can write your own. This is a very popular one, the drag pulse, and so that's the one we're actually using here.
Exactly. Good, so now we know what our Rabi experiment does and how it does it. So then we go on to our options, which are, as before, accessed from the experiment workflow. I again increase the count a little bit. I say that I want to use calibration traces. I say that I want to update, even though it's already calibrated. And then I say that I want to calibrate the G transition. I could also put EF here. So let's run this. And then in this demonstration, we run the Rabi experiment on all the 3 qubits of this QPU in parallel. So here we pass a list of amplitudes, the same for all the qubits, but they also can be different depending on how you want to define this. And here the amplitude is not in volts. It's really just a scaling factor with respect to this output range of the instrument, which is now 10 dBm.
Yeah. So here, depending on my setup and architecture, I can either run serially, so one at a time, or I can run in parallel on all my qubits. And the same was also true for the qubit spectroscopy, I guess. Exactly, so I can also do that in parallel.
Exactly. We demonstrated there for 1 qubit as the first demonstration, but you can pass many qubits. So let's run the Rabi. Again, we get all the logging information to check what is going on. And then the execution time now is 20 seconds. You can reduce this by reducing the averages. But here we wanted to see a good signal. So let's wait. Yes. And then all the analysis tasks that were run, it's telling you that it saved all these figures. So let's look at what it produced. And here we have again all the JSON files and the Rabi plots. So in this case, for qubit 1, you can see then for qubit 2 and for qubit 3. So these were done in parallel. You see they have different pi pulse amplitudes because the oscillation frequency changes. And you see on the y-axis, we have the excited state population, which was inferred from these calibration traces shown here by the dashed lines. And then we fit this cosine model to the oscillation and extract the new pi pulse amplitude and pi half pulse to induce these rotations.
Great.
Yeah, thank you.
So also you might notice we're going into the folder structure to show you kind of how everything is saved. You could also have these appear in your notebook. There's a lot of ways to configure this for what works best for essentially your experiment, right?
Exactly, and we show a lot of this in our tutorials and in our how-to guides. Just look at the manual.
Great. Well, thanks a lot, Steph. Next, I'll be talking with Simon Cross, who will tell us a bit more about the architecture and some of the design choices that we've made when making these updates to the LabOne Q software. Thanks.
Thank you.
So we're back with Simon. In the last segment, Steph and I did some tune-up experiments, and we saw in those experiments that we used some new functionality of LabOne Q, tasks, workflows, and quantum operations. Simon, thanks for joining me. Can you give us an overview of these new parts of LabOne Q that we've introduced?
Sure. So when you're writing software generally, whether for quantum experiments or for other reasons, you want to structure what you're writing, and these new concepts we've introduced are to help structure the experiments and experiment workflows that are being built on top of our devices, and to provide tools for our users to do that. So quantum operations provide an abstraction where you can write things which are more like gates, so you think in terms of operations on qubits. And then tasks and workflows allow you to organize the bigger pieces that go around your real-time experiment, such as your analysis and kind of calculations based on the experiment outcomes.
Cool. When you say, can we focus first on workflows? So workflow is a word that's used all over the place. Can you explain what we mean by workflows?
Yes, so workflows are a very overloaded term within software, and they can mean very different things. Our workflows are very lightweight. A workflow in our context is a Python function that defines a graph of tasks to execute, and a very small engine that runs within the Python process, which executes that graph. So it's not a big complex tool that runs on a server somewhere. Those can be useful in their own realms, and you can use our workflows as building blocks for these bigger systems. But we've focused just on a tool for our users to use to organize what they are doing.
Cool. When you mention workflows and tasks, so workflows can execute tasks, and as I understand it, they can also execute other workflows. Can you explain the difference between workflows and tasks themselves?
Yes, so a task is really an ordinary Python function. When you run a task, it runs exactly the Python you've written. A workflow then is when you run a workflow, it's also a Python function, but when you run it, it builds a graph of tasks to execute later. And then when you call .run on your workflow, it actually executes it. And you can, as Ken just mentioned, you can have tasks inside workflows. Workflows can also have sub-workflows.
Cool. Coming back to now the quantum operations, so how have we implemented quantum operations in our framework?
Sure. So what a quantum operation is, it's a Python function which takes in qubits or other quantum elements and uses those to define the pulse and signal operations needed to perform that quantum operation. The way that you work with this is that you as a person with a quantum device would define these operations in terms of signals to play on the device. And then when you're writing your experiments, you would call these quantum operations so that, for example, if you're writing just a simple amplitude Rabi, you would define a Rx operation, which would take in a qubit and an angle, and you would then call that operation inside your, say, your Rabi create experiment task, and this would allow you, when you're reading that Rabi create experiment task, to see a few simple lines which correspond exactly to your high-level picture of how Rabi works. So you prepare your quantum state, you play an Rx gate with a given amplitude, you perform a measurement, and then afterwards you perform some calibration measurements. And so really in 5 or 6 lines, which make it very clear what the experiment is doing, you can see what's happening, and then you still have full control over the pulses that are played in your by defining your quantum operation.
So the quantum operations are kind of a natural way at the gate level, if we want to say it that way, to work with LabOne Q. So instead of just working at the pulse and signal level.
Yes, exactly. So the quantum operations allow you to work at the gate level, although you can also perform qubit-based operations that perhaps would not necessarily be considered gates in the ordinary sense. For example, you can write a operation that changes the flux bias via a third-party instrument, and that can also be a quantum operation, even though it's not, say, the traditional Rx, Ry, or Z, C0, etc. gate.
Got it. So you also mentioned qubits and quantum elements earlier. How do these fit into quantum operations? Or how do they interact with quantum operations if they don't fit in, I guess I should say?
Yes. So quantum operations and qubits go together in that when you're writing a quantum operation, it acts on one or more qubits. Practically, you would start by defining your qubit class, which really is a list of the parameters that you keep track of for your qubits. And then when you write your quantum operations, it's another class that you write. Each operation is a method on that class. And inside that method, you access the qubit parameters. So for example, if your qubit has a pi half amplitude, then when you're playing an Rx, when you're writing the Rx gate, you will use that calibrated amplitude parameter to calculate the the amplitude for your RX gate, given the angle that was provided.
Cool. So now if I'm thinking about kind of the bigger picture, so I have my quantum operations, I have my qubits and quantum elements, I have my tasks and workflows. How do I take these together to either do an experiment on a single qubit, 2 qubits, 100 qubits, 1,000 qubits? Because we know that if I want to do just a single qubit experiment or even a 2 qubit experiment, these aren't the same. Now I have, with the 2 qubit experiment, I have a 2 qubit gate. If I have a couple more qubits, then I may have things like crosstalk. So how can I use these tools to actually address the problems as you're scaling up?
Yes, so there are genuinely hard problems to be solved in scaling up the control of quantum systems. And our software is not going to take away these fundamental challenges, but what it will do is provide with the tools so you don't also have to solve a bunch of software challenges. So if you started out with a simple tune-up experiment that acted on 1 qubit, and you will see this in our examples in the LabOne Q applications package, you don't have to change anything to increase the number of qubits. You just supply a list of qubits to your tune-up experiment, and then you can increase increase the length of the list.
Yeah.
And so there you can easily go from, say, 5 to 10 qubits. As you go up to 100 qubits, many hundreds of qubits, there will be more crosstalk challenges. There will be many other effects that you have to take care of. But the challenge that you shouldn't have to solve is how to structure your experiment definitions, and that should remain largely the same as you scale up.
Okay. So the structure will remain kind of constant then throughout, let's say, an arbitrary number of qubits for these tune-up experiments. Can you talk a bit more about, for implementing workflows, you had mentioned earlier that they're lightweight. How is this important for actually working with workflows when you're scaling up as a researcher?
One thing I forgot to mention on the previous point is it's a very useful concept provided by the quantum operations when scaling up is the concept of broadcasting a quantum operation. This concept might be familiar from other languages like OpenQASM, but you can apply a single quantum operation to many qubits in parallel and without changing the structure of your code. But yes, let's talk about the scaling up and the workflows.
Yeah.
So the lightweight workflows are a step towards scaling up. So as mentioned, they allow you to structure things in prepackaged ways. But because the workflows are lightweight, you can use them in a Jupyter notebook, but you can also run them just in an ordinary Python process. You can also run them as part of as a building block in a more complicated system, say some sort of automated tune-up or some sort of user-accessible web service. So these are tools which are helpful even scaling kind of to
just a few qubits.
To a few qubits.
Yeah.
Yes.
So if you're a user even at a small number of qubits, these workflows really can still be useful for you for the way you execute your experiments. And if you're familiar with that, and then you go to many more qubits, so not just 5 or 6, but lots and lots, then they remain useful. So the structure remains the same.
Yes.
Cool. Can we return a bit to the difference between workflows and tasks? So if I am a user and I want to write my own tasks or own workflows, what are some of the subtleties maybe that I should be aware of?
Yes. So when we built these tools, we completely have the intention that the users will write their own tasks and workflows, and we provided kind of documentation going step by step through what's needed to build these yourself. So if you're writing a task, you largely decorate it with an @task decorator, and then what you write inside is reasonably kind of ordinary Python. You take in inputs, the workflow will ensure the inputs get passed in, and then you return your your outputs, and it's very much normal Python. If you're writing a workflow, you have to just think a little bit differently. You also write a Python function, you decorate it with a workflow decorator. But then in your Python function, you're describing the tasks to run and how inputs and outputs from one task are passed as inputs to the next. And when that function is executed, it uses this description of which outputs are used where to decide on how to order the tasks and how to execute them.
Yeah, so this sounds really useful now when I'm doing a real experiment and working with data. Can you also tell me a bit what we've updated in terms of the saving and loading functionality and how workflows can help you essentially do all of your data handling, and if I want to then connect workflows, do multiple experiments together, where this fits in?
Yeah, so one of the reasons for building an execution graph rather than running ordinary Python is that this execution graph gives you a lot more visibility and control into of what is happening. And so you could imagine that as a scientist, it's very important to know in a lot of detail what your experiment has done. And so while a workflow is running, it logs each task that is executed, and also it saves to disk the inputs and outputs of each task, so that when a workflow finishes, you have a complete scientific lab book showing you what happened, and you can then open the folder where that is stored in an ordinary file browser, or you can open it from your Jupyter Notebook if that's kind of where you're working, and images are saved in standard image formats. Things like NumPy arrays are saved using NumPy standard data format. LabOne Q objects like experiments and compiled experiments and experiment results are just saved using the standard LabOne Q functions. So this logbook is really meant to provide you a long-term scientific record that you could access kind of days or weeks or months later, even when when newer versions of software have been released.
Yeah. And what happens if for some reason there's an error during one of the tasks, let's say in a workflow? Can I pick up where I left off? Do I lose the data? Do I not lose the data? What happens there?
So that's one of the advantages of having this execution graph. So if an error occurs, you can call a recover function, which will allow you to access the results which have been calculated or have been produced so far. Mm-hmm. And if your Jupyter Notebook is still running, you can do that within the Jupyter Notebook. But if the whole Jupyter Notebook kernel crashes, all of the data that has been produced so far will have been saved to disk, and you can go and kind of inspect it and load it as normal.
Okay.
You can also specify a point in the workflow to stop running and then to resume from there. Mm-hmm. So if you wish to run part of a workflow, examine the intermediate results and then continue, that's also made possible via the workflow engine.
Great. Well, we're going to see how this works in practice. So we're going to be back with Steph, and we're going to look at how to write your own experiment workflow. So before we've actually gone over the Rabi and the Qubit spectroscopy, but now we're gonna look at what happens if you want to write your own. Thanks very much for taking the time, Simon.
Thanks, Kent.
Yeah, and thanks, and we'll be back soon. So now we're back with Steph. And Steph, what are we going to do now?
Thank you, Kent. So now I want to show you how to use the tools of LabOne Q to write a new experiment like the ones in the applications library. So let's say you just want to write your own, or there's something we do not provide yet. You can easily write a new experiment workflow and a new pulse sequence using this physics-focused syntax with quantum operations and qubits.
Cool. So the experiment this is not an experiment that's currently in the applications library. This is really a characterization experiment to see how, with two qubits connected by a coupler, that if one, and we're driving them at the same time, if one is in the excited state, how it can affect the frequency and therefore the phase of another qubit.
Exactly. So let's get into it. And I have a template here just to not spend time writing too much. This is the experiment workflow for the residual ZZ coupling that we're going to write. So here we just decorate a function with this workflow decorator, giving it a name. And then we write the input parameters, here again the session, the QPU, the qubits, and the phases. So we're going to sweep over phases as I will, phases of a pulse as I will show a bit later, and the options. And then again, we follow the usual structure of these experiment workflows. We create the experiment, and this is what I'm going to write. Then we take the compile experiment task and run that. Then we run this compiled experiment and we return the result. So this is what I want to write for you and show how you would do it. To turn a Python function into a task that can be used inside workflows, you simply decorate any function with this task decorator that lives in the workflow namespace imported from LabOne Q. And here, in addition, we have another decorator called Qubit experiment. And when a function is decorated with this experiment, it expects to find some qubits in the inputs, and from those qubits and the DSL domain-specific language from LabOne Q to create the sweeps and the acquire loop, this decorator knows to combine all of that information into an experiment object in LabOne Q. So this is the object that contains the information about the pulse sequence that we're going to write.
So here we're going to use instead of the pulses on signal lines, we're using these constructs of the QPUs and the qubits and the quantum operations to define our sequence. So
exactly. So first, I will just assign these quantum operations which live in the QPU to a shorter variable, so I can work with it a bit easier. Then already here I've written the acquire loop with counts, so the number of averages, and the counts come from the options, so you can change them. And then the sweep over the phases, and this is a sweep parameter, standard LabOne Q construct you can learn about, and the alignment for it. So this is usually something you write for most experiments that do sweeps. So now we want to create this residual Z characterization measurement. So what are we going to do?
Yeah, so as Steph is coding here, maybe I can explain the experiment a little bit. So we're going to have two pulses. They're both 90-degree pulses. So we're going to start in the ground state of one of the qubits, and we're going to apply a pulse, and then we're going to wait for some time, and then we're going to apply another pulse. Both of these pulses are 90-degree pulses, so we're going to go from, let's say, along the z direction to in the plane. And then we're also going to prepare the other qubit in the excited state. And what we're going to do with the pulse on the first qubit, the second pulse on the first qubit, I should say, is we're going to sweep its phase. And what we'll see, so we're going to have then two plots, essentially. We're going to have one in which the first qubit we're sweeping the phase, and the second qubit will be in the ground state, and we'll see an oscillation. And in the second plot, we're going to have the qubit in the presence of the second qubit in the excited state, and we're also going to sweep its phase. And what we'll see is in one case, there will be a phase difference between these two plots because of the residual ZZ coupling. And that's exactly what Steph is typing here.
Exactly, but here I've written some sections. So the quantum operations by themselves, maybe I can show you what this a quantum operation output. So you can call these in your notebook QPU quantum operations. I choose X180, so you can also see what they are. If you do keys, this is the set that we have now defined. So Rx, Ry, Y180, X180, the usual single qubit gates. And then if you put one of the qubits inside and call this, it returns one of these LabOne Q sections. And inside there's reserved signals for all the signal lines of this qubit, except for the drive line where it applies a pulse. So it's a play command with this amplitude and length and the drag pulse that we've defined in the qubit parameters.
Yeah, so this is all inherited from the qubits themselves.
Exactly.
And here you have a missing eye.
Exactly. Thanks for catching that.
Yeah.
And the point here is that you can also choose to omit this section. So you have full control over the timing, right? So here I've chosen to make a big section around the drive. So as Kent explained, when the state of one qubit is either on or off, we iterate over that. We make a drive section. If the state is on, we apply an X180 on one of the qubits and do this phase measurement. So sweeping the phase of the second X90 pulse on the other qubit, and we have a delay. And then finally we do this measure operation on both the qubits. So I actually do for Q and qubits, and then here Q and handle. This is the
essentially
name.
the string
Exactly.
we want to save it under, more or less.
Exactly, and the library actually provides you some nice result handle, calibration trace handle, so you don't have to. You can also put the string here, like create your own, but for standard handles, the library provides this for you. And then finally, a passive reset.
Great. And so as you're coding this up, both at the pulse level and at the gate level here, there are a lot of tools even offline that you can use to inspect this. So your time on your QPUs is valuable. So if you want to prototype this offline, you can. And then you can already inspect what the pulse sequence will look like and what the output of the instrument will look like without even being connected to the instruments. So that's what we'll also show you, so that by the time you go to run on the qubits themselves, then you know and are confident that you're going to output the right thing.
Exactly. Here I realized that this section was outside of the iteration over state, so I've just moved it in. Let's execute this cell. And then we have our usual cell that executes this workflow and builds it. So here we sweep over quite a big range from 0 to 4 pi in 51 steps. And we do it on qubits 1, 0, and 1, which are connected by a coupling resonator. And as Ken said, so first maybe you want to, you've just prototyped. You want to see, does what I write make sense? You don't want to run the full thing. So you say, please stop at the compile experiment. Of course, I've probably made some typos here, exactly. That's always happens when you prototype, right? Okay, so this only ran up to the compile experiment and stopped. So then you get the compiled experiment out of the tasks that were run. So on the workflow result, tasks, the name of the task, and the output returns you the compiled experiment of LabOne Q. And we can look at the pulse sheet viewer. I actually want to, while we look at this, to run the measurement because it takes a bit of time. So we say, please resume. So we've run up to the compile and then resume. So please continue and execute on the hardware. While we do that, let's look at the pulse sheet.
Yeah. And the pulse sheet here is really kind of a cartoon of boxes. And what the pulse sheet viewer shows is each individual box is a LabOne Q section. So these are timing constructs within LabOne Q. And it gives you an overview of a very kind of broad overview of what your experiment looks like on the whole. And what the pulse simulator does, which we'll show afterwards, is really what you can ask the question, okay, it's nice to see this kind of cartoon, but what do the signals coming out of the instrument actually look like with their absolute timing? You can also use our simulator tools to do that. So here we have the pulse sheet viewer.
Exactly. So you see the sections that we've created and the pulses here on each of the lines. So here we have the two X90 pulses on qubit 1 and the excitation pulse on qubit 2. We have a long passive reset of 200 microseconds, so I'll skip over that. And then in the next iteration, there's no pulse on qubit 2. So we measure this phase on qubit 1 when qubit 2 is excited or not. If you want to see the actual pulses that you've programmed, the shapes, so here we have this plot simulation, as Kent explained, and we look at the drive and the measure signals just to filter some of the noise out. And you see again the two X90 pulses on Qubit 1, and then Qubit 2 has this excitation pulse here.
Yeah. And if we go back to the pulse simulator and we scroll down a little bit, we can also, these two tools are actually combined in your interactive pulse sheet viewer, so you can both generate static HTML, but if you're using the one that's embedded in the notebook, you have the signals, and then you can click on an individual pulse, so maybe just choose one of the RX pulses, and then you can actually inspect the pulse themselves, and you get both. Here you see the absolute timing, and in the pulse sheet viewer itself, you also get the samples that it comes in on, so both the samples and the timing. So with all these tools, you really have exact, precise control, and you can really inspect what you've done before you're even starting to run.
Exactly. Thank you. And now let's see the data that we got. So here I wrote already a bit of code just to extract the results from the workflow output. So I go and say, please look at Qubit 1, the result for it, and we've given this suffix in the handle to know when the other qubit was in the excited state or not. And if I plot this, we see that there's a clear phase difference between the oscillations that we've measured for Qubit 1 when Qubit 2 is excited in orange or not in blue.
Great. Well, thanks a lot, Steph. This really shows the power of these tools that have been introduced in LabOne Q. And if you have more questions, please drop us a line or leave them in the comments right now, and we'll try and address all of them. Thanks.
Thank you.